Yesterday when we were together, we took a look at making quick graphs of linear functions. We were concentrating on generating 2 points so that we could quickly graph those functions. One way was using slope-intercept form, where the intercept is 1 point on the line, and the slope allowed us to find another point on the line. Second method we used was called standard form, and with that we were able to identify x and y intercepts, which were 2 points on the line, use those to graph the line quickly. Today we're interested in writing equations of lines. First, from slope-intercept form. If we know the slope and the y-intercept, we can plug those in to y equals mx plus b, where m is the slope and b is the y-intercept. That's pretty straightforward, so we're not actually going to do an example of that one today. But I do want to look at another form of equation called point-slope form. And we're going to just define that, the linear equation in the form y minus y1 equals m times x minus x1. So we've got a jumble of letters here, just alphabet soup. Big important thing, there's 3 inputs. The first is your slope, and the second is a point, which comes to us as a set of coordinates, which we're going to call x1 and y1. We take the x coordinate from the point that we're given, plug that in for x1, the y coordinate from the point that we're given goes in for y1, the slope goes in for m, which will give us point-slope form of a linear equation. Let's take a look at an example. Given the point -4, -1, and a slope of 2, write the equation of the line that passes through that point and has that slope. I'm a very large fan of writing down the formula, whether it's a math word problem, whether it's a physics problem, other type of science problem, writing down the formula and then plugging in values. So, y minus the y1, the y coordinate of our point, which is -1. Don't lose that negative sign. We're going to actually put that in parentheses. Equals m, which is our slope number, 2, times the quantity, x minus our x value, which is -4. We know that subtracting anything is the same as adding its opposite. So y minus -1 is y plus 1. Slope number 2 remains the same. Same situation here. X minus -4 gives us x plus +4. We've been kind of trained when we see this situation here to use the distributive property and simplify. We don't have to. It's a perfectly good linear equation in point-slope form. Y plus 1 equals 2 times the quantity x plus 4. You could go to slope-intercept form if you wanted. Then you would distribute. 2 times x is 2x. 2 times 4 is 8. The left side of the equation is y plus 1. Now we solve it for y. Subtract 1 from both sides. Y equals 2x minus 8. That's the exact same linear relationship expressed in 2 different forms. We can do this again quickly just to see that this sign does not always change. These signs only became positive here, unlike the general form, because both of our x and y coordinates were negative. Here I've got a point -3, 5, and a slope number of -4. Let's plug those in. Our y is +5, y minus 5, equals the slope number -4 times x minus -3. Y minus 5 equals -4 times the quantity, x plus 3. And as above, you don't have to simplify this. You can leave this in this form. It's a perfectly good linear equation called point-slope form. In both of these cases, we were handed a point and a slope. Not always going to be the case. For instance, write an equation of a line that passes through the point 6, -2, and is parallel to the line y equals 2x minus 1. And we have a point, but we're not given our slope value. But with a little bit of detective work, we can find it. This is y equals mx plus b form. My slope value is the multiplier on x. My slope is 2. So I have a point, 6, negative 2. I have a slope value of 2. Y minus y1 equals m times x minus x1. Y minus negative 2 equals 2 times x minus 6. We simplify here, y plus 2 equals 2 times the quantity x minus 6. Similarly, write an equation of a line that passes through negative 1, 1 and is perpendicular to the line y equals negative 3x plus 4. Well, what are we going to do here? Perpendicular to. I know that a slope that's perpendicular to another slope is going to be a negative reciprocal. Looking at my equation, I have a slope value of negative 3. I need the negative reciprocal of negative 3. First, I need the reciprocal, which is negative 1/3. The negative reciprocal will change its sign. This will be positive 1/3. So the slope that I want to work with is positive 1/3. We'll set this off and call this side work. Okay, now, y minus y1 equals m times x minus x1. We've got our slope. We've got our x and y coordinates for our point. Let's go ahead and substitute those in. Y minus 1 equals 1/3 times x minus negative 1. Simplifying, y minus 1 equals 1/3 times x plus 1. Finally, we do want to take a look at a word problem, an application of point-slope form. What we'll find is, in particular, when we're asked to be able to make some predictions about years in the future, or working backwards towards a date in the past, the point-slope form allows us to easily substitute in a value. So our word problem says in 1995 there were only 6 California condors living in the wild, all in California. In 2006, there were 138 California condors living in the wild in California, Arizona, and Mexico. We're asked to write a linear model that represents the numbers of California condors living in the wild between 1995 and 2006. Well, let's start there. Write a linear model. What are they asking us for? When we are trying to model this situation with math, we're thinking that it can be represented in a linear relationship. We can write a linear relationship as an equation. This problem is asking us to write an equation. Let's look at what information we have. We have a date, 1995, and a number of birds, 6. A date, 2006, and a number of birds, 138. So we can write these as ordered pairs. Our question is, which is the dependent variable, which is the independent variable? Well, it seems that the number of birds depend on the year. So let's make the number of birds our dependent variable, our y coordinate. In 1995, 6 birds. In 2006, 138 birds. The example shows us that we can now take that rate of change and write it as a slope. 138 minus 6, our change in the dependent variable, divided by 2006 minus 1995, the change in our independent variable. And that gives us a value of 12, which as a rate of change is our slope. Now, we can use our point-slope form to represent this as a linear model. Y minus y1 equals m times x minus x1. Do we have a slope? Sure. It was given to us as part of the setup of the problem. Do we have a point? We not only have one point, we have 2. You can select either one you want. I think most of my students prefer to deal with the numbers that are a little bit smaller. So let's use our first point we were given. Y minus 6 equals the slope number 12 times x minus 1995, the x1 value. this would be our linear model. If we were asked perhaps to predict how many California condors might be in the wild in 2011 or 2020 or 2050, assuming a linear relationship, we could plug those values in, the year in for X, solve for Y, which would give us a number of California condors in the wild. So that is using point-slope form to write an equation of a linear function.